Okay, a bit of a warm-up before we get started on everything. Just a bit of review on how we can do some things. We had talked, I don't even remember what unit it was, about what percent of your data is within 1 standard deviation, within 2 standard deviations, within 3 standard deviations. That was our empirical rule. But if you forgot it, now that we have the tools for finding these probabilities, you could just straight calculate it. So if I wanted to remember what percent is within 1 standard deviation of my mean, you could use your normal CDF. So you would say you want to be from -1, so 1 standard deviation to the left of the mean, all the way up to +1, 1 standard deviation to the right of the mean. This is the standard normal curve, so we're going to use a mean of 0 and a standard deviation of 1. When you put that in, you still get the approximately 68% we had been using. Before we were rounding it to the nearest percentage, so that was to the nearest hundredth place in decimal terms. But now we could actually get a little more accurate because we have the calculator to do that. Likewise, if we don't remember the total area under the standard normal curve, we could just say, I want it to go from -infinity to +infinity. Since we don't have a button that represents infinity, we have to just use a very, very small number and a very, very huge number. So by using -1e99, that is standing for -1 times 10 to the 99th. -1 with 99 zeros at the end of it, all the way up to 1 with 99 zeros at the end of it. So standing in place from -infinity to +infinity, still in the standard normal curve, so we have a mean of 0, standard deviation of 1. When you put that in your calculator, now technically it should be 0.9999999999999999999. I bet that's really annoying to listen to on a recording, but your calculator automatically rounds it up to 1. Because we can't go to -infinity and +infinity, it's only approximately equal to 1, even though the whole curve is exactly equal to 1. So a couple things, your homework assignment from the previous day of applying it to different probabilities. Check your answers here. So just to make sure you're doing the right thing, pause the video, go look at your work, make sure you're getting the right stuff. And if not, go back and fix those, because what we're doing today is the reverse of the stuff we were just doing. So we are still going to be using normal distributions, but now we're going to be finding a z-score given area under the curve, and changing that z-score into an actual value from the data, and using this data value, finding this data value given some probability. So for example, if I tell you an area and I want the z-score, you're not going to use normal CDF because that's how you found the probability, that's how you found the area. We want to do the opposite of that. And the way your calculator does the opposite of that is something called inverse norm. If you go into your calculator exactly where you found normal CDF, the feature right below that, mine is option number 3. It literally says inv norm, which stands for inverse norm. When you put that in, you will need to tell it the cumulative area. It will only ever use the cumulative. If you don't need the cumulative area, you will have to figure out what area you actually want. So this is the area to the left of the z-score we're going to find. Then we put in the mean. Since it's a standard normal curve, we're going to be talking about 0 and 1 for the mean and standard deviation. And the reason I know it's a standard normal curve is because we're talking z-scores. Z-scores only appear on the standard normal curve. Actual x values occur on the just regular normal distribution. So by putting that in and rounding to the nearest hundredth, we can find that it matches up with a z-score of approximately -0.44. So then for part B, find the z-score that has an area of 0.9616 of the distribution's area to its right. Now, if you look at what I typed in, I'm not putting in 0.9616 because that's the area to the right. And if that much of the area is to the right, then the complement of that is to the left. And again, inverse norm only works with cumulative areas. So this is the area that is to the left of the z-score that we're going to calculate. So 1 minus 0.9616 gave me that. Still using 0 and 1. You can find a z-score, which makes sense that it should be negative. If 96% of your data is to the right of it, you have a z-score that is pushed to the left of the mean, pushed to the left of 0, so it's negative. So now when we talk percentiles, percentiles divide a data set into 100 equal parts, which means, for example, if they tell you some 6-month-old is at the 78th percentile for weight, then that infant weighs more than 78% of all other 6-month-old infants. So that percentile is the cumulative area below their value. So if I want to find a z-score for this, if I'm told that it's the 5th percentile and that's notated as p sub 5, we would find that using inverse norm. Since it's cumulative, you just turn it into a decimal and you say you want to do the inverse norm. You want to do the opposite of finding the area. You want to find the z-score that correlates with that. So 0.05 with 0 and 1 is your mean and standard deviation. So I'm getting negative 1.64 for my z-score. P sub 50. So in your calculator, that would be the inverse norm 0.5, 0, and 1. Now, that is finding the z-score that puts 50% of your area to the left of it. You do not need a calculator for that because we've talked about how the mean is in the center of your distribution here. So 50% of it has to be to the left of it. So I'm talking about the mean, and on a standard normal curve, that z-score, that mean, is just 0. You can get 0 out of your calculator too, but you shouldn't need to do that. So then P sub 90 would just be inverse norm of 90. You get about 1.28. Now that's all well and good, but it's not super helpful if you can't translate it to actual values, if I'm talking weights, if I'm talking like miles per gallons or years or something. So using your z-score formula, we said z is equal to x minus mu over sigma. If we solve this for x, the first thing you would do to get x by itself is you'd move sigma. And since it's currently saying divide it by sigma, let's just multiply both sides by sigma. So z times the sigma is equal to x minus mu. Now to finish getting x by itself, you're just going to add mu to both sides. So you can find any x value by taking your z-score times the standard deviation and adding the mean to it. So that's what I'd like to do right now. I'm telling you the mean of the monthly utility bills. I'm telling you the standard deviation. We're going to find the x values if you know the z-scores. So using that formula, I'm going to take the first z-score, negative 0.75, going to multiply by the standard deviation and add the mean onto it. This is undoing finding how many standard deviations away it is. So we found that the x value would be 64. If you have a value of 64, it is 0.75 standard deviations below the mean. So if I use 4.29, that's a lot of standard deviations above, and we find out it's 104.32. It's significantly higher than the mean. And negative 1.82 would be below the mean. You can find that it's 55.44. So that means if we get a scenario like this, we could actually find a score rather than just a z-score. So a mandatory competency test for high school sophomores has a normal distribution with a mean of 400 and a standard deviation of 100. The top 3% of students are going to receive a reward. What is the minimum score you'd need to receive the reward? Award, reward, whatever. So if it's the top 3%, then we need to think what's the area below this cutoff score. So if it's the top 3%, 97% is below. So what we can do is inverse norm 0.97, 0, and 1. This is finding a z-score since 0 and 1 are telling me it's on the standard normal curve. But it wants the minimum score on this competency test. So we need to take the z-score and change it back into an actual real score. So using that formula we were just saying, just plug it back in. 1.88 times 100 plus 400. We can find that the score would have to be 588 in order to put you in the top 3%. Now, because this is off the standard normal curve, that's the way we just did this. But you could treat it as if it was on the normal distribution. So instead, if you still type in inverse norm, still type in that cumulative area. If you don't use 0, if you use 400, if you don't use 1, but you use 100, you are taking it off the standard normal curve and just putting on one specific normal curve. This means you're not going to find a z-score. You're going to find an actual x value for the problem that correlates with that percentage, with that 0.97 to the left. And you still get around 588. So you're getting the same answer, you're just going about it a different way. The one nice thing about doing it the second way, in addition to being less steps, so I guess 2 nice things, is you're having to round a lot less. This 1.88 was rounded. It was not exact. So then when you go to use a rounded answer, I should have approximate equal signs here. You're rounding your answer even further, causing potential mistakes. We're going to be rounding x values to the nearest whole number here, so it's not going to be an issue so much for us, but it could potentially be. It's just good practice to round as least as possible. So for the same test, the bottom 1.5% of students have to attend summer school, and I want to know the minimum score that you need in order to stay out of this group. So you could do inverse norm with that score. I missed a comma, 0 and 1. You'd get a z-score because 0 and 1 are telling me it's on the standard normal curve. Then you could take that z-score and change it back into an x value and get the cutoff score. Or you could bypass all of this if you would just use the mean of 400 and the standard deviation of 100. It still rounds to the same answer. So then for this scenario, to qualify for security officers training, recruits are tested for stress tolerance. Scores are normally distributed with a mean of 62 and a standard deviation of 8. If only the top 15% of recruits are selected, we're going to find the cutoff score. So rather than going through and finding the z-score, let's go directly into finding that score. We're going to still use inverse norm because I'm giving you the percentage. When you calculate percentage, it's normal CDF. When you're given the percentage and finding the z-score or finding the x value, that's when you use inverse norm. So if we jump into using the cumulative area, so if it's the top 15%, we're talking about the lower 85%. Since it's the standard norm, it's not the standard normal curve, but just the normal curve. I'm not using 0 and 1. I'm using the given mean and the given standard deviation. And that finds for us that it's a cutoff score of 70 for the top 15%. So that should be all you need in order to work on the assignment. Good luck, and hopefully you have questions that you can ask. Have fun!